Okay, so I am very excited to introduce our next speaker. Her name is Lisa Levin. She's Professor Emeritus at Scripps Institution of Oceanography and at UC San Diego, and she's going to be speaking to us about deep sea mining. So there's a lot of discussion about mining underwater in the jewelry industry. Most of it's very light on the real implications. So we brought a real expert to talk to us about this. And Lisa, I'd like to welcome you to the stage.
Okay, is this working? Everybody can hear me? So hi, everybody. I'll be honest, I'm a scientist. This is the first time I've ever spoken to a group of jewelers. And I'm really hoping that I can just open your eyes to a new world that's out there and tell you a little bit about the debates that are going on about deep seabed mining. I can't see very well because I have a bright light in my eyes, but how many of you feel like you're at least a little bit familiar with the seabed mining issue? Okay, not that many people, just a few. Okay, well, hopefully at the end of the next half hour or so, you'll know more. And you're going to see that you're going to feel like you're sitting in class or something because I'm a professor and that's how I talk to people. But, focus on the pictures and the main messages. Okay, so let's see if this works. What I want to do is talk a little bit about the deep sea in general, basic science, because most people don't know much about it. And then I want to home in on hydrothermal vent ecosystems, and that's what you see in the movie there. And that is because people are now thinking about sourcing gold and silver at hydrothermal vents. And we call this, some people call it a gold rush. Other people have other names for it. But I will talk about deep seabed mining, what it is, and what some of the issues are that are being debated, and some of the conservation-related issues in particular. So, full disclosure, I'm a deep sea biologist. That's what I do. I'm also an oceanographer. I'm only in the last decade gotten interested in the policy implications of what I do, but now I'm fairly involved in the policy aspects. Okay, so let's start with the deep ocean. For us scientists, the deep ocean is anything below 200 meters, or about 600 feet. And not surprisingly, that's actually most of the ocean. It's about 95% of the habitable volume on this planet. So most of this planet is deep ocean. Even by surface area, half the planet is deep ocean. So it's a big chunk, but it's not very well known. Less than 25% of the deep ocean seafloor has been mapped, and this means that we actually don't know most of the biodiversity that's out there. So it's one of our big frontiers. And the other thing that you see on these figures is that about 36% of the ocean is within national jurisdiction. That means exclusive economic zones, which go 200 miles from everybody's shore, are national waters, but about 2/3 of the ocean is in international waters. And it has a completely different jurisdiction and governance regime, and I'll talk a little bit about that because that affects deep seabed mining. Okay, so this is the ocean. This is Scripps Institution of Oceanography, where I work. If you look at the ocean, you see the same thing that almost everybody does, no matter whether you're standing on a small island in the Pacific or in the Indian Ocean. You look out and you see this vast expanse of blue. And most people don't know what's underneath that, right? Except what you see on NOVA and National Geographic and so on. So we all are really limited by our perceptions. And most people talk about the deep sea like it's one thing, like the deep sea, right? But just like the land is not one thing. The land is mountains and deserts and canyons and plains and, amazing things. The deep sea is exactly the same. It is full of a host of different ecosystems. And I've depicted some of them up here. There are ribbons of low oxygen zones that I spent a lot of my career studying that run along the continental margins, sometimes covered with bacteria. Actually, do I have a pointer on this? I think I don't, do I? Okay. There are vast abyssal plains that go on for thousands of miles, just sort of like our plains on land, and they are covered with those potato-sized nodules that I'll come back to, that people are interested in mining. There are tens of thousands of underwater volcanoes called seamounts that dot the seafloor and have really dense aggregations of corals and other animals. There are thousands of canyons and fjords that cut our continental margin, just like we have canyons on land. They are cut into the deep ocean, and again, they also have aggregations of animals. Some of the deep water animals are corals and sponges, and they can form their own habitat. They can form reefs that are many kilometers long and host many other animals, so they're an important source of biodiversity. And we've discovered that there are ecosystems that rely on chemical energy rather than sunlight and photosynthesis, and those are called chemosynthetic ecosystems, and the methane seeps and hydrothermal vents that I've depicted there are examples. And they all occur in very deep water, not that deep, but fairly deep. And then we have the water column. That's all the water that sits above the sea floor. And there are what we call pelagic ecosystems there. And these are probably the least explored. There are many animals, jelly animals and fish and crustaceans, all different kinds of animals that live in the water, deep water as well. So these are just a few of the kinds of ecosystems out there. Each of these systems hosts their own species, their own biodiversity that are different from the next one. And over the years, and we've really discovered many of these only in the last 50, 60, or 70 years, but one of the things we found is they also host a wealth of resources that people are interested in extracting. So for example, the oxygen minimum zone bacteria sequester phosphorus, and it forms phosphorite, and people are now interested in mining this as a source of fertilizer. The abyssal plains host these potato-sized nodules called polymetallic nodules, rich in cobalt, nickel, zinc, and copper. And there, as you'll hear in a few minutes, there's a lot of interest in mining these. Probably most relevant to this conference are the massive sulfides that are precipitated at hydrothermal vents that are rich in copper, zinc, lead, gold, and silver. Again, interest in mining. The seamounts form these thick crusts. They're called ferromanganese crusts that are rich in cobalt, nickel, molybdenum, and cerium. And there's interest in mining these. The canyons aggregate organic matter over millions of years. That forms oil and gas, and we're very actively extracting that now from our deep canyons. The seamounts have aggregations of fish, which are harvested. The orange roughy you see in this picture is an example. There are fish that hang out at methane seeps as well. For example, the Chilean sea bass or Patagonian toothfish is one example. And there are many fish that use coral and sponge reefs as nursery grounds, like rockfish that we harvest commercially. So these are examples of some of the resources that people are interested in harvesting from the deep sea. And they're now looking at a new fishery for the very small mesopelagic fish, which by the billions migrate up and down every day. And there's some interest in harvesting them for fish meal. So all of these systems most of these systems share a number of features that distinguish them from systems on land or even in shallow water. One of the features is that the animals can be really, really long-lived. So a deep sea fish might be on average between 100 and 200 years old, but these are actually really young compared to some deep sea corals, which can be 4,000 or 2,000, 4,000, 5,000 years old. And the oldest known organism is a sponge, I think dated at 17 or 18,000 years old. So this is kind of mind-boggling when you think about organisms living this long, but they're not disturbed in most cases. There's also a lot of heterogeneity. I showed you all these different ecosystems. They're very patchy on the bottom of the ocean, each with their own endemic species. Many of them depend on very specific hydrologic or geochemical properties, the oxygen, the chemical content of the water. So if we disrupt that, those species get disrupted. There are a lot of what we call mutualistic interactions. That means where one species depends on another. So if we harm one species, it means that we've probably altered many others at the same time. And there are also really strong connections between the deep sea and the surface ocean, and most people don't realize that. But anything we do at the surface can affect the deep ocean fairly quickly. And the same thing, if we affect the bottom, we can also change the aspects of the surface ocean. And I'll talk a little bit about that. Okay, so that's deep sea, what I call deep sea fundamentals. Now you all hopefully know a little bit more about the deep ocean than you did. And I want to talk about hydrothermal vents. These are places where water circulates inside the Earth's crust and then it's ejected as a thermal spring that's warmer than the ambient water. So most deep sea water is somewhere between 2 and 5 degrees centigrade. And the hydrothermal vents can be 20 degrees centigrade, or they can be super hot, like 389 degrees or 400 degrees centigrade. And the reason they can get so high when water boils at 100 is the high pressure. So water doesn't boil at 100 degrees when it's under very high pressure. And as you've seen from these movies, they host a lot of really interesting organisms, which I'll talk about. This is a map of hydrothermal vents. All the red and yellow dots are them. They occur along mid-ocean ridges, which are places where new Earth crust is formed and the plates spread apart. And they're also formed in back arc basins where some subduction occurs. And you can see that they kind of form along lines in the Atlantic and the Pacific and the Indian Oceans. There are, as you can see, about 400 known hydrothermal vents. The very first one was discovered in around 1976 or 77. So, in the last 50 years, we've discovered a lot of them, but it's estimated that many remain undiscovered, and there's probably 1,300 or so of them. That's just a prediction. And they're really interesting environments. They're very small and patchy. People believe they hold a clue to the evolution of life on Earth because the conditions are so extreme. The pressure is high and the temperatures are also high. 80% of the species known from hydrothermal vents only live at hydrothermal vents at these tiny patches. The animals have really important adaptations. I'll talk in a bit about their bacteria. But these tiny patches sit on ore deposits, which are formed when the hot water meets the cold water and precipitates called massive sulfides occur, and that's where the gold and silver sits that people are interested in mining. Most hydrothermal vents have big animals that dominate, and so in these pictures up here you can see the upper left tube worms, and below them clams, and below them mussels, and then to the right massive numbers of shrimp, or large numbers of snails, or large numbers of crabs. So in any one place, the diversity might be low, but each vent has, different vents have different species, depending on what ocean they're in and what part of the ocean. And these big animals are reliant on bacteria that use chemical energy to make their food. We call this chemosynthesis. And so these animals, all the ones you see here, have the bacteria living within them or on them as symbionts. So we call this symbiosis. And those bacteria use sulfide and methane that's coming out of the vents to fix carbon and feed the animals. And that's the reason that the animals at vents are so big. Those tube worms you see on the upper left with the red plume, they're like a meter long, sometimes even more than that. That's really big for a deep sea animal, where most animals are small from lack of food, but at vents they got a lot of food. So they have really unusual adaptations, and they've all evolved different ways of living with bacteria. From the snail to the alvanellid worm you see there has basically a coat of bacteria on its back. Some of the crabs have them on their stomachs, and the shrimp farm them on their claws, and the tube worms have them in a whole organ that runs the length of the tube. So hydrothermal vents can be actively venting, like those smokers I showed you the movie of, and they have the big animals, or they can be inactive, where the ore and the massive sulfide sits there and it's colonized by other kinds of animals like corals and sponges. We're just now learning that there is this thing we call a sphere of vent influence that reaches far beyond the vent field that we see. We are finding that vents are interconnected to each other by subsurface conduits, and they're also connected by surface currents and the movements of animals. And on the inactive vents, which are one of the important mining targets, we're realizing that those animals, the corals and sponges, are actually benefiting from the nearby active vents and from the food that moves away between them. Vents have these what looks like smoke in the water, but it's not really smoke. It's small particulates that precipitate when hot water reaches cold water, and they're called hydrothermal plumes. And these emissions rise from active vents, and they form distinctive seawater layers that harbor unique chemicals and form connectivity highways for animals and larvae of animals, the early life stages that move between the vent patches. And vents are also, and these plumes export nutrients, including iron, which actually fertilizes the whole ocean. It's a very important source of iron, and it's a key to having a productive ocean and all the fish and fisheries and everything else we take out of the ocean. So there are many different ways we value vents, and when humans value something, we call them ecosystem services, if you haven't heard that term. And I just talked about some of the biogeochemical cycling that goes on, sulfur, nitrogen, and iron. The animals and their bacteria are fixing carbon, so they're an important part of the carbon cycle. Some of the microbes have really important properties that are of industrial application and maybe even solutions for climate change, because some of them eat carbon dioxide. There are biomimicry interests at vents. The scaly-foot snail I showed you a picture of is being used as a template for new kinds of armor for cars, airplane hulls, and so on. We know that vents provide habitat and food web support to a huge wealth of biodiversity. Minerals, of course, are precipitated there, so there's interest in gold, silver, copper, and a few other metals. Vents are an important source of education and outreach and science, but they also have a more spiritual value and existence and bequest value, which is something that future generations may want and need. And we're still discovering new vents, and we're still discovering new functions at vents. So within the last few years, we've discovered skates and rays lay their egg cases at vents, even though we don't even though the adults don't really live there. We don't know why. They use it as a nursery ground. And I don't know if any of you have seen the pictures of the massive numbers of octopus that are now found brooding their eggs at warm water on seamounts, which are sort of mini vents. And so remember that song, The Octopus's Garden? That turned out to be true. The deep sea has all these octopus's gardens there, and there's several of them that have been found on the East Pacific. Okay, so now you know about the deep sea, you know about hydrothermal vents, and now I want to come to seabed mining and tell you what it is. You can see these scary looking machines, and you see the people there, so that gives you some idea of how big they are. I mean, mining is basically extracting minerals from the deep sea floor, and it involves either cutting up the seafloor rocks and sucking them up to the surface, or vacuuming them up in the case of nodules. So there are 3 ecosystems targeted for mining in international waters. Oop, that didn't work. Let me go back and see if I can get, no. I don't think I can get the movies, all the movies to work now again. Let's try that one more time. Somebody's going to turn them on for me. Thank you. So I mentioned seamounts and abyssal plains and hydrothermal vents. So polymetallic nodules on the plains, ferromanganese crests on the seamounts, and massive sulfides at the hydrothermal vents. And as you can see, they're each really different ecosystems with different species, and in many cases different minerals, but they are all now being targeted for mining. And you can just enjoy these incredible pictures of, for anybody who tells you there's nothing in the deep sea that would be affected by mining, don't believe it. Here's, living proof. You can see it with your own eyes. These amazing organisms are down there. And these are all types of habitats targeted for mining. Okay, so these mineral resources are really widespread. The hydrothermal vents are the orange dots, but the nodules are in blue, and the seamounts and the cobalt-rich crusts on seamounts are in yellow. So you can see they occur in all of the oceans. But we'll home in on the polymetallic sulfides. But before that, I just want to show you a map of who owns the ocean, okay? I mentioned that beyond 200 miles, we have international waters, and that's all the pink area you see in this map. And the UN Convention on the Law of the Sea created an agency called the International Seabed Authority, and access to minerals in international waters is only through the International Seabed Authority. They are supposed to act for the benefit of mankind, and the minerals are on the seafloor in the international waters are considered the common heritage of mankind. And that means that everybody owns them on the planet, all of you guys included. And the International Seabed Authority, or what we call the ISA, is in the process of gearing up the mining of these minerals and managing all the signatories of the Law of the Sea, establishing mining regulations and so on, and establishing the financial regulations. So over the past few decades, the ISA has authorized 31 international mining exploration contracts in all the areas you see here, for all the different types of resources that I've been talking about. And you can see which countries are involved. Over to the left of Mexico in the Pacific, there's this big cluster of 19 or 20 countries that have contracts in the Clarion-Clipperton zone for polymetallic nodules. In the West Pacific, over on the right side of this map, you can see Russia, Japan, China have, in green, have seamounts for exploration areas for ferromanganese or polymetallic crusts. And then the red are the hydrothermal vent contracts In the mid-Atlantic, it's Poland, France, and Russia. In the Southwest Indian Ocean, it's South Korea, India, Germany, and China. And they are sort of these long linear features because the vents run in patches along linear features. And this is sort of a picture of who's interested in mining in international waters right now. These are exploration contracts, so there has not been any exploitation yet. They are in the process of developing the regulations for exploitation, and when that's done, mining is likely to begin. Okay, so those, I've circled the 2 hydrothermal vent ones where you need to be on the lookout for gold and silver, maybe. But there is interest in mining within national jurisdictions as well, and I've shown just a couple of places where that could happen. There were many, many leases in Papua New Guinea, and back 10 years ago, a company called Nautilus was planning to begin mining, but they went bankrupt and left Papua New Guinea with a very large bill. And my understanding is that there are other companies that have come in to fill the void and take over these leases, but I don't know Papua New Guinea's plans. Everybody thought we would have deep seabed mining of hydrothermal vents in 2013 or 2014, and it hasn't happened yet. New Zealand also has leases on its shore for hydrothermal vents in the areas you show in red, just north of the northern part of New Zealand. And Japan has hydrothermal vents in the Okinawa Trough in its own territory, and it has actually done test mining like 5 or 6 years ago. But as far as I know, they haven't begun any commercial mining, but these are countries to keep your eyes on. I want to talk a little bit about what mining might do to the ecosystems where it occurs. It's extraordinarily disruptive, just like it is on land. And it involves removing what we call the substrate. That means the rocks or the sediments or whatever is there, and that's where the animals live. So if you remove their surface, they don't have a place to live. Mining changes the topography, the shape of the seafloor. It changes the texture of the seafloor. And all of this can affect biodiversity of the seafloor in a negative way. Genetic diversity, species diversity, habitat diversity, and so on. Mining also removes the big animals that create three-dimensional structure that hosts other animals. So these big corals or tube worms or mussels all have a biota that lives on them. Many, many other species depend on them. So that's another way that biodiversity is lost. Mining changes the geochemistry of the environment, and it's that geochemistry that the microbes depend on that fuel the entire ecosystem. So just like we live off a system based on plants, it vents, all the animals live off ecosystems based on bacteria. And so mining will change the kinds of bacteria and their ability to support life. Mining alters sediment plumes. In some of the environments, like the nodule environments, it creates big sediment plumes that were never there in the deep waters. But at hydrothermal vents, there's already sediment plumes created naturally, and not sediment, there's hydrothermal plumes created naturally, and mining probably alters those, and which affects animals in many ways that we don't even know yet, because we haven't even characterized all the biodiversity in these systems. We do know that the great longevity, slow growth, slow maturity of animals means that they are not going to recover from mining very soon. Hydrothermal vent animals at active vents can grow a little faster, but at inactive vents, they grow very, very slowly, and at all the other ecosystems like seamounts and the nodule zones, they grow very, very slowly. So this means that once you mine, the disturbance will probably last for centuries or longer. certainly longer than a human lifetime. And we also know that and I don't have it on a slide, but restoration is not possible like it is on land. We don't believe it's possible. The vents occur at thousands of meters water depth. The nodules occur at maybe 3,500, 4,000 meters. That's 12,000 feet. Doing restoration in these environments with super slow growing organisms is just not economically or feasible, and not feasible in terms of timescale. And we know that many of these systems, especially the hydrothermal vents, are spatially patchy. We know that animals depend on source populations from another vent, and they exchange larvae. So when you destroy some of the vents, you run the risk of causing local extinctions or maybe global extinctions. And there's also a lot of exchange between the bottom and the surface that I mentioned. There are animal migrations that go across entire ocean basins. There are larvae that move from the seafloor to the surface and back down as part of animal life cycles. And so mining is likely to interfere in many different ways, not just by disturbing the bottom, but by releasing water up in the water column, releasing contaminants from the water. There was a paper recently that shows radioactivity gets released from the nodule zones during mining, and there's a lot of sound and light and vibration that's not normally there that will disrupt marine mammal migrations and turtle migrations and anything else happening in those waters. So there's lots and lots of sources of disturbance. I've sort of summarized them on this slide: sound, light, vibration, geochemistry, substrate, food webs, contamination, and physical disruption. So mining is highly disruptive, and there is a lot of biodiversity on the seafloor that could be disrupted. But we don't know everything that's there, and we don't really have in our knowledge box all the information we need to manage an industry like seabed mining. So we're missing information about who's there and how they're distributed, what their life histories are, how long they live exactly, how they reproduce. We know very little about the animals in the water column or the ones that live at inactive vents. They're not as charismatic, so scientists haven't studied them much. We know mostly about the northern hemisphere systems, and the APIs are actually the ISA's protected areas, but they haven't been studied. We don't know much about connections between populations, how they vary in space and time, and we don't know all the functions and services these ecosystems provide. We're still learning about these. And we also have a lot of knowledge gaps that are more applied. Like, we don't know what constitutes serious harm, and that's a legal term in the law of the sea and in the mining code that would cause mining to stop, but it's not been defined yet. We don't have good indicators of a healthy system or the threshold values for the harmful effects of mining, and all of that is somewhat in progress, but it's definitely not there yet. We don't know if you mine in one place what the spatial extent of it is, how far the mining plumes or the contamination will move. Will it move out of the mining contract area to another country's coastal waters? A lot of the Pacific island nations are worried about that. We don't know how mining will affect other ecosystem services like fisheries or carbon cycling, for example. We believe there are extinction risks, but the very specifics aren't known. We have no clue about whether these systems really can ever recover. We think it would be slow. We have no clue how to do restoration. And there are other kinds of cumulative impacts like climate change, overfishing, other contamination problems that might compound with mining to affect deep sea ecosystems. So where we're at now is that there really isn't enough knowledge to do evidence-based decision-making in line with the International Seabed Authority obligations to protect the marine environment, because they are obligated to do this, but we don't really know how to do this. And we do risk destroying deep sea biodiversity before we discover it and understand it, because so much of that biodiversity has yet to be found. It is truly one of our planet's greatest frontiers. Given everything I've told you, it's not surprising probably to hear that there has been a movement for a moratorium on deep seabed mining. Some people call it a precautionary pause. And this gives you the country history. It really got off the ground not that long ago, about just over a year ago, with Fiji, Palau, and Samoa proposing a 10-year moratorium on mining while we gathered more scientific information and really decided if we needed it. And then you can see Chile, Costa Rica, Ecuador, the Federated States of Micronesia, and Spain joined shortly after that, this movement, then New Zealand, then France, Germany, Panama, then Vanuatu and the Dominican Republic. And I believe there may be one or two other countries, Canada and maybe some others, that have joined this movement. But it is still a small group of countries, maybe 15 or so. And there are 162 countries that have ratified the law of the sea. And for a moratorium on mining to actually happen, the International Seabed Authority Assembly would have to vote not to mine. And that's probably not close to happening yet. And we'll see what happens. But it's not just countries that are voicing their opinion. A number of companies have come out for a moratorium on seabed mining, and you can see them here. There's some car companies, Google, Patagonia. There are some fishing organizations, a lot of NGOs, non-governmental organizations, not surprisingly, and a lot of indigenous groups. And then there's a number of countries that have vowed not to source deep sea metals, including Microsoft, Ford, Daimler, GM, and relevant to this group, Tiffany and Company. And I don't know if there's any other jewelry companies that have weighed in on this issue. And then there is a letter from 704 deep sea scientists calling for a pause to deep sea mining while more science gets done, because really there's rather little that's been done. Okay, so that gives you a picture of deep sea mining. I guess, let me back up 1 minute and just say where we're at is that the International Seabed Authority, 2 years ago, Nauru and the Metals Company triggered this little rule called the 2-year rule that says that the regulations for international mining have to get done, or they're going to submit an application for commercial mining, and it has to get approved. That's a rule in the law of the sea. So they triggered that rule 2 years ago, July. The 2 years came and went, and the regulations and the mining code is not ready yet. And there was a lot of concern that the metals company would just submit an application this July, but they haven't. And the ISA has agreed that they need another year to get the code ready. So we're looking now at another year till probably there is any kind of mining application approved, or maybe even more. As this moratorium movement grows, it's still not going to stop the International Seabed Authority, because the law of the sea says that we can mine. It's important to realize the law of the sea was written before we knew very much about the ocean. We weren't worried about climate change when it was written, and we hadn't discovered hydrothermal vents or methane seeps or a bunch of these ecosystems, including some of the ones they want to mine. They weren't even discovered. People believed those minerals were sitting amidst a desert with little to no life, but you've already seen that's not the case. Okay, so there are other resources in the deep sea that might be that are of interest to the jewelry industry. And I would say diamonds in Namibia, many of you are familiar with that. They're not mined from the deep sea. They're mined down to about 200 meters, which is sort of the edge of the deep sea, but it's it's still kind of relevant. And then precious corals, I don't know where they all come from, but that deep sea corals are also a potential source for the jewelry industry. Okay, so I'm just about done here. And these are my main messages. I hope you understand now that the deep ocean hosts a lot of different ecosystems, many with resources that are vulnerable to human extraction. And among these are the hydrothermal vents that have precipitates of gold, silver, and copper. Active hydrothermal vents are really small, globally rare sites where hot fluid comes out and it sustains ecosystems, and they have been designated by ocean managers as vulnerable marine ecosystems, but that hasn't really stopped the International Seabed Authority from issuing exploration contracts. Globally, vent habitat is estimated to occupy only about 50 square kilometers, so that's a pretty small area. I should mention that the resources from fossil hydrothermal vents on land are actually much greater than in the deep sea. So mining in the deep ocean for vents doesn't make a lot of sense. The abundant endemic life provides a lot of different services, and some of the animals, especially at inactive vents, are long-lived and vulnerable to mining. And deep-sea mining is highly destructive, as I've been saying. One of the things I didn't talk about was the motivation for mining beyond jewelry. A lot of people believe that to combat climate change, we need metals for electrification of our transport system and for electric car batteries, metals like cobalt and nickel. And that is driving a lot of the interest in mining the Clarion-Clipperton Zone. And one of the things to say about that is that, and the belief is that mining these in the deep ocean is much better than mining them on land, because no people live there and no people are harmed. But it's very complex, and this group knows very well there are livelihoods on land dependent on mining. It's not a simple issue. We're also, the battery technology is changing so fast that the need for lithium cobalt batteries is going away. Some car companies aren't even sourcing and using those metals anymore. They're using iron phosphate batteries. So the technology is changing. The land miners I talk to say nickel and many of the other resources are available on land, and the mining technology on land is improving, as well as the social conditions and so on. We are doing a better job of recycling. We're also working towards reducing demand for the metals. So there's a serious question about whether we need deep sea metals and whether we need to go into one of the planet's most pristine environments to get these metals. It may be in 10 years that we've sort of moved beyond nickel and cobalt, which is driving a lot of the mining interest. Okay. And with that, I'll thank you. If you're interested in this topic and want to learn more about it, got cut off at the bottom. This is the Deep Ocean Stewardship Initiative is an organization that I helped to found that addresses human impacts. It's basically a network of scientists that bring science to policymaking in the deep sea. There's a minerals working group that is very active on the mining front, and there's a whole lot of information. There are information sheets and policy briefs and short courses and all sorts of things that you can get off our website at dosi-project.org. With that, I'm happy to take any questions. I realize I talked for a long time.
Hi there. Thank you so much. That was super informative and quite jarring, to be honest. You mentioned diamonds briefly, and what I'm wondering about is I'm seeing certain companies that are trying to set themselves apart from the deep sea mining by saying that they are mining in shallower water and that they're positioning those impacts as much lesser than the mining in the deep sea. Some even using language such as saying the diamonds are hand-picked, even though there's still small machinery that is involved in vacuuming up the gravel and such. So I'm wondering, what do we need to know to be able to dispel these claims? Because I'm assuming that it's not exactly accurate to say that the impacts are significantly lesser.
Well, they are different in that I'm not aware that diamonds are coming from very deep waters. They're coming from the continental shelf, where things grow faster and can recover faster. And there are, of course, important ecosystems in shallow waters, but we do a huge amount of sand and gravel mining in the same vein. We pull it up from our continental shelves, and we dredge our harbors to make them deeper so ships can go through. So we do a lot of shallow water disturbance. I am not able to say that diamond mining, in shallow water is not harmful, but I don't think it's the same scale, as the organisms aren't living for hundreds to thousands of years there, and the environments aren't as normally pristine and undisturbed because there are other kinds of influences of people, contaminants from land, and so on. That's really all I can say about that. But it's very interesting to me to hear that companies are positioning themselves as not deep sea mining, because that makes a big statement about deep seabed mining, even from the industries. Yeah. Are you calling on people, or am I?
If you have the mic.
Hi, I've got it. I got it. Thank you so much. That was amazing. Quick question. I noticed Apple wasn't on the list of companies that have eschewed deep sea mining, and I'd like to get it on there as a big Apple user. Any suggestions for how we add more companies to that list?
Yeah, I'm not involved in that aspect. There are quite a few NGOs that do that kind of work. I'm just a scientist, but what? Okay. Well,
Excuse me.
so yeah, because our cell phones have a whole lot of rare earth elements and other things that people are trying to get from various places. So I don't know. Apple must have a sustainability officer, right? Somewhere I would go to them. Siri, yes, ask Siri.
I have a question. I'm over here. Fabulous talk, very fascinating. Thank you for coming and speaking to us. Many of the people in this room are from the United States, and I noticed that the U.S. had not been given any exploration contracts for deep sea mining. And I was just curious if you could tell us anything about the U.S.'s involvement. Also, continental shelves, what are Americans up to? And just, I know we kind of just talked about Apple, but Tesla, any thoughts on that?
Okay. Tesla actually doesn't use the same kind of, I think they're one of the groups that have switched to alternative batteries that don't use deep sea minerals, I think. Wait, the first part. Yeah, the US. Okay, so we have not ratified the law of the sea, along with many other international treaties. The US doesn't like anybody telling them what to do. And so we actually don't have access to the international minerals, despite the fact that we were studying polymetallic nodules for mining before the law of the sea came into being in the Clarion-Clipperton zone, where all the other people have exploration contracts. Now, it's kind of a long story, but that was Lockheed Martin doing that in the 1970s. when they could not get an exploration contract because of the US status, Lockheed Martin opened a subsidiary in Britain which had ratified the Law of the Sea. So it was called UK Seabed Resources, and they got several contracts in the Clarion Clipperton Zone to mine. So Lockheed sort of went in back door. But you know, mining is a very expensive and long-term thing, and I think Lockheed Martin just sold its contracts to Loke, which is a Norwegian company, and has gotten out of the mining business as far as I can tell. So the US in international waters has like no role now. The Norwegians want to mine, I should have put them on the list, they want to mine their own waters, and now they have contracts in international waters. So the Norwegians are all gung-ho about mining, which go figure, because they're such big ocean advocates. In terms of US state waters, I was just at a meeting yesterday and I was asking somebody from the Bureau of Ocean Energy Management, which does our oil and gas and our seabed and our gravel mining and things like that. And they said they're gearing up to look at whether there are mining opportunities in the US waters and whether there's industry interest. So we definitely have the resources. I've done research on phosphorites and ferromanganese crests off Southern California. They're there, but so far no company has said they want to mine them. But that could be coming. I mean, we have presidential mandates for exploration of mineral resources in US waters. So it could be happening, and definitely, I'm sure you guys know, there's gold mining in Alaska, that's going on that's also controversial. But it's not in the deep sea, so I'm not that familiar with it.
We have time for one more question.
Great. Thank you so much. That was so such a perfect introduction to this issue, because I didn't know a lot about it. And I realize the question of why is very simple, but could you share more about the motivations for this other than because the resources are there? Just what are some of the other motivations for deep sea mining?
Well, the main one now being proposed by the metals company that wants to mine polymetallic nodules in the Clarion Clipperton Zone is for electric car batteries, because they claim we need 1 billion electric cars to achieve the energy transition, to combat climate change. So that seems to be, at least if you read what they're saying, that seems to be the main motivator. I think money is the real motivator. And nobody will do it if it's not going to be economically beneficial, right? They would continue to mine on land. And there are a lot of nickel and other resources on land that are in reserves that are available. So that's a motivator. And then the argument that it's so much less damaging to the environment than on land. But the other thing I didn't make a case about, because I focused on vents, which are tiny, but the polymetallic nodule contracts are enormous. They're like thousands and thousands of square kilometers for one contract. So they're orders of magnitude bigger than landmines. And the resource is right at the surface. So it would basically vacuum up the top meter of seafloor over areas that are tens of thousands of square kilometers. So in one contract in the Clarion Clipperton Zone, in 1 year of mining, would be 2.5 times the size of the biggest coal mine in Germany. I mean, it's just phenomenal. And then after its 20-year lifetime, it would be like an order of magnitude, 10 or 100 times the size of land mining. So we're talking about much, much bigger scales of mining, especially for polymetallic nodules. It's debatable about whether we really need the minerals, about whether, or will need the minerals by the time they're in short supply because of changing technology. And the other thing is the common heritage of mankind. The Law of the Sea intended for these resources to benefit developing countries, but the companies and countries that are going to mine wouldn't generate much monetary benefit to the rest of the world. People have done calculations, and it's really a small amount of money that would go to various countries of the world. And the people who will really benefit are the multinational mining conglomerates that are working with every country. I mean, only countries can sponsor international mining, but behind each one is a mining company. And sometimes they're state mining companies, like in China, but sometimes they're commercial companies, like Nauru is working with the metals company. And though the metals company is based in Canada, I believe, but it's definitely North American wealthy. And so the real benefits to these resources would not go to the originally intended common heritage, but the damages to the environment would go to the common heritage of mankind, and all the world would suffer from the loss of that biodiversity and its services. That's my opinion about it.
Thank you so much. That was phenomenal. It's such a privilege for us to be able to get exposure to this information. So thank you. Thank you so much.